Yes, good morning, students. Am I audible?
Yes, ma'am.
So here we were in the module 4. So we have left with some of the topics. So here we need to discuss about the dimensions of the four subspaces and the linear transformation and then orthogonality. So three topics are left. So here today we'll discuss dimensions of the four subspaces, linear transformation and some problems on this we're going to solve. So here first let us start with the dimensions of the four subspaces. So here we have seen what is vector space, what is subspace. So here in many problems they may ask to calculate the four fundamental vector spaces given the vector. So you may ask to calculate the four fundamental spaces, subspaces. So here we'll see what are those subspaces. Already we have solved so many problems on that. So here once again we'll just revise which will be called as the four fundamental vector spaces and what parameters you need to calculate. So here subspace, it can be described in two ways. One is the given set of vector which is going to span the space, and the second one is the condition of the vectors in the space must satisfy. So here we used to calculate the conditions on B. So here for what values of B, the equation Ax is equal to B is going to be solvable. So here depending on that, so here it can be described in two ways. So here in the vector space we'll come across four subspaces. So here the first subspace is the column space. So here the column space of the matrix A, it is denoted as C of A and its dimension is nothing but the rank R. So here we'll see how to calculate the rank R for the column space. The second one is the null space of A, which is denoted as N of A and its dimension is N minus R. And the third one is the row space of A, which is nothing but the column space of A transpose, which is taken as the column of A transpose and its dimension is R. And the fourth one is the left null space of A. It is nothing but the null space of A transpose such that when we solve the equation A transpose Y, it must result in 0 and its dimension is M minus R. So here suppose in the problem if you ask to calculate the four subspaces, so then you need to calculate the column space and the null space of A and the row space of A and the left null space of A. So column space is nothing but you are going to calculate, you are going to identify the pivot and from that you will be identifying the column space. And the second one null space, it is nothing but you are going to solve the equation like Ax is equal to 0. So here in that you will be identifying the null space. And the third one, which is nothing but the row space, it is nothing but you are going to take the transpose of the matrix A and from that you will be identifying what is the row space. And similarly the fourth one, so which is called as the left null space, it is nothing but the null space of the A transpose. So if you ask to calculate these four subspaces, so these are the parameters you need to calculate in the problem. And here, for example, here we have taken row space of A. So here instead of this, we'll take one problem and directly we'll solve that. So take the problem. Find the four fundamental subspaces for the matrix A, which is defined as 101 in the first row, in the second row 2, 1, 2, and in the third row we have 3, 1, 3. So given this matrix, we asked to calculate four fundamental subspaces. So here as I told, four fundamental subspaces in the sense, so whatever column space, row space, null space and the null space of transpose vector, that has to be calculated. So here we'll see how to calculate that. So here first let us consider the matrix A, which is defined by 1 0 1 2 1 2 3 1 3. So on this matrix, so we are going to apply the row echelon form. So row reduced form. So here some linear transformation methods are going to be applied in order to make some of the rows as 0. So here we are going to apply R2 minus 2R1 and R3 minus 3R1 as well as R3 minus R2. So when we apply these three transformation, so here you can see that it will be resulting in the matrix 1 0 1 0 1 0 0 0 0. So this is the reduced form of the given matrix A. So once you get this matrix A and the reduced form of matrix A, then we can go for identifying the 4 fundamental subspaces. So the first one is the column space. So here column space is nothing but, so here wherever the pivots are present. So here if you observe the row reduced echelon form, so here the pivot is present in the first element of the first row, and the second pivot is present in the second column of the second row. So here the corresponding column, so they will be considered as the column space. So here 1 0 0 and 0 1 0. So they are represented as the column space. So here we can write column space of A is equal to 1 0 0 0 1 0. So wherever the pivots are present, so identify those as the column space. So once you write these elements from the row reduced form, so corresponding to this, choose the elements from the given matrix. So here 1 0 0, it corresponds to the column 1 2 3, and 0 1 0, it corresponds to the column 0 1 1. So here actual column space for the matrix A, it is 1 2 3 and 0 1 1, and the dimension of this is nothing but 2. So here since 2 column spaces are there, so here the dimension of the column space of the matrix A is 2. And the next one is row space. So here row space, so in order to obtain this, so here take the transform of whatever the row reduced form you have obtained, as well as the matrix A. So for matrix A and the row reduced form, take the transpose. So here you can write what? Row transpose, it can be written as, so row transpose is nothing but column elements will be shifted to the row and row elements will be shifted to the column, right? So here 1 0 1, which is in the row, so that will be written in the column, and 0 1 0, which is in the second row, that comes to the second column, and so on. Similarly, you just perform the transpose on the matrix A. So here the matrix A elements, which is given with 1 0 1 2 1 2 3 1 3, so it will be transposed like 1 2 3, and next you will be having 0 1 1 and 1 2 3. So after this, once you get this, so here write the column space of A transpose. So here the column space of A transpose is nothing but, so here you need to compare this. So here you can see that the 0 is present in the third column. So excluding this, you need to write the column space of the A transpose, which is nothing but the row space for the matrix A. So here we have 1 0 1 and 2 1 2. So here non-zero ellirutte. So non-zero columns in the corresponding A transpose in the pick madidre, so you will be getting the row space, that is 1 0 1 and 2 1 2. So here the dimension of this also is 2. And the next one is null space. In order to get the null space, we need to solve the equation Rx is equal to 0. So where R is nothing but the reduced form of the matrix A. So in the reduced form of the matrix A, we have this matrix, that is 1 0 1 0 1 0 0 0. So here we are going to write that. So X is nothing but the variables x1, x2, x3. So when the matrix multiplication of these R as well as X, it should result in the value 0. So here when we do that, when you simplify this, so you can see that 1 into x1 is x1 plus 0 into x2 is 0 plus 1 into x3 is x3. That is x1 plus x3, it is equal to 0. So this is the equation 1. And similarly from the second row, so here 1 into x2, so x2 is equal to 0. So yes, x2 value is obtained, so it is directly given as 0. And since we have in the second expression as x1 plus x3 is equal to 0, so here which implies that x1 is equal to minus x3. So now from this, so we can write the equation for x as x1, x2, x3, which is equal to, so here x1 is nothing but it is equal to minus x3. So here in place of x1, we are writing minus x3, and x2, it is 0 here, and x3, it belongs to the R. So here we are writing x3. So here x3, it can be taken outside. So x3 within the bracket minus 1 0 1. So once you get that, so if the null space of the matrix A is minus 1 0 1. So this is obtained by equating Rx is equal to 0. So this is the null space of the matrix A, and here the null space is just containing one column, so the dimension will be 1, and it can be cross verified like, so null space of dimension of null space of A is equal to n minus R. So here n is nothing but number of rows we have. So that is no number of columns we have 3. So here 3 minus 2, that is the rank of the matrix is 2. So here since now if you observe this, so here it is containing 1 0 vector. So here excluding this 0 row, so here the rank of this matrix is taken as 2. So here since 2 non-zero rows are there, the rank of this matrix is 2. So here 3 minus 2, it will be resulting in 1. And the last one is we need to calculate the left null space. So in order to calculate the left null space, we need to take the transpose of the matrix A. So here the transpose of the matrix A, it is given as 1, 2, 3, 0, 1, 1, 1, 2, 3. And this apply the linear transformation function. That is some transformation function, elementary functions we are going to apply. So here we have applied R3 minus R1. So once you do this, so it will be reducing to 1, 2, 3, 0, 1, 1, 0, 0. So here this has to be, so here whatever the equation that we have obtained, so A transpose, so here we need to solve A transpose Y is equal to 0. While explaining the 4 subspaces, we have seen this equation. We need to solve A transpose Y is equal to 0. So here we have this Y transpose, A transpose. So this has to be multiplied with Y. So here Y is nothing but y1, y2, y3. That is the variables. So here solving this matrix, so here you can see that it will be resulting in, so y1 plus 2y2 plus 3y3 is equal to 0 and y2 plus y3 is equal to 0. So here this implies that y2 is equal to minus y3. And also since we have obtained y1 plus 2, y2 plus 3, y3 is equal to 0, simplifying this, so it will be resulting in y1 is equal to minus y3. So now once you get the values of y1, y2, y3, so you can go for writing the elements of y. So here previously we have written x. So here now in this we have taken it as y. So here y, it is given as y1, y2, y3, which is obtained as, so since y1 is equal to minus y3, so in place of y1 you are going to write minus y3, and y2, so it is also obtained as minus y3, so minus y3, and y3 is a free variable. So free variable in the sense it will not be having the pivot. So whatever the concept that I have told previously that you need to remember. So here you can see that pivot is present here, that is in the first row and also in the second row. So here this y1 and y2 which contains the pivot variables, so they will be considered as the dependent variable. And in the third row, so we do not have any pivot elements. So here the corresponding whatever the y3 variable we have, so that will be considered as the free variable. So here that will be belongs to R. So here we can write y3. So here y3 can be taken outside, and within the bracket we can write minus 1, minus 1, 1, and this represents minus 1, minus 1, 1. It represents the null space of the A transpose matrix. So here the dimension of this, it is also equal to 1. So here you can see that. And similarly, you can have some more problems like, so here the same problem, the similar problem we are given here, find the dimension and the basis for the 4 fundamental subspace. So once again, consider this matrix, you just go on with the methods. I will be sending these notes. So you just work on this, and if you have any doubt, you can contact. So here, after this 4 fundamental spaces, so next we left with linear transformation. So now we'll discuss linear transformation. So before this, so here one problem on the dimension and subspace I would like to show you. So here we are given W as the subspace of R5, so which is spanned by x1, x2, x3, x4, x5. So here you can see that x1, so x1 elements 1, 2, minus 1, 3, 4, they are written along the row wise. So you may get the question like it has to be written along the column wise. So no matter, you can write either in the row wise or the column wise, it doesn't matter. So only the thing is you need to remember, so whether the column is representing the elements of x1 or the row is representing the elements of x1. So here all the elements x1, x2, x3, x4, x5, so we have written row wise. So here x1, x2, x3, x4, x5. Whenever I will be saying x1, x2, x3, x4, x5, so they will be representing the row elements here. So for this, we are asked to calculate the subset of vectors which is going to form a basis of W, and also we'll see the calculation of the dimension. So here for this given matrix A, so here transformation functions are applied elementary operations are performed. So here you can see the various operations that are performed. So for all this, you need to show the matrix. Only directly I have written the answer here. So, but you need to show each and every step for every step answer in the solution. So don't directly write in the test or in the exam. You will not get the marks. So here when you mention the operation like R2 minus 2R1 and R3 minus R1, so you are supposed to show the result here. For each and every operation, you need to show the matrix values. So here, after applying all this, so here the reduced form of the matrix A, so it is obtained as 1, 2 minus 1, 3, 4, 0, 0, 1, 3 minus 1, 2, 0, 0, 0 minus 4, 0 minus 5. So here you can see that 2 0 rows, row vectors are present and the remaining 3 non-zero rows are there. So here whatever the non-zero rows you have obtained, so that will be representing the dimension. So here the dimension of this vector subspace is 3. So ಎಷ್ಟು non-zero rows irutte, so that is nothing but the dimension and the corresponding elements. So here x1 x2 is 0, leave that. X3 x4 is 0, leave that. X5, so here x1 is containing the non-zero row, x3 is containing the non-zero row and x5 is containing the non-zero row. So here x1, x3, x5, they are going to form a basis in the W. So similarly, one more example is shown here. So for this also you are going to identify the dimension after applying the row reduced form, and also you are going to identify the basis for the given vector. So the next topic is the linear transformation. So here first we'll see what is linear transformation and why it is required. So here in mathematics, whenever you will be considering the linear transformation, it means that it is a linear map which is used for mapping V to W between the two vector spaces, which is going to preserve the operation of vector addition as well as scalar multiplication. So we have to see that it is going to preserve its structure. So structure in the sense, so once you transform the function x1 to x2 transform madidira antandre, so but along with the transformation it has to preserve the operation like vector addition as well as the multiplication. We should be able to apply those operations. And also here the linear transformation, they are very useful because they preserve the structure of the vector space, and many qualitative assessments of vector space which can be considered as the domain of linear transformation may be used under certain conditions. For example, we can use to hold the image of the linear transformation. So here having that basic definition, so here if you consider V and W as any two subspaces over the field, scalar field F, and a mapping T, so the mapping transformation function, it is denoted as T. So here the mapping T from V to W, it is called as the linear transformation. As I told, it has to preserve the addition as well as the multiplication. So here it is called as a linear transformation if the first condition is if V1 and V2 belongs to vector space V, and the transformation on V1 plus V2, it should be equal to transformation of V1 plus transformation of V2. That is, we are applying the linearity property, you can say. And the second one is for all A belongs to F and for all V belongs to V, then the transformation applied on the dot product of A and V, it must be equal to A multiplied with the transformation of vector space V. So in other words, we can say that the transformation on A1 V1 plus A2 V2, it must be equal to A1 transformation of V1 plus A2 transformation of V2, and for all A1 A2 belongs to F and for all V1 V2 belongs to V. And in general, we can say that transformation of summation AI Vi, it is equal to summation AI transformation of Vi. So here whatever the diagram you are going to see, so here we have V space and the W space. So in the V space, we will be having the various elements like V1, V2, V1 plus V2 and A into V and so on. So on these elements, you are going to apply the transformation function. So T is going to be applied. So the transformation function, it may involve the various operation, like it may be differentiation, it may be integration, and so on. So whatever may be the transformation, so once you apply that, it has to satisfy the addition as well as it has to retain the addition as well as the multiplication property. So here you can see that, so V1 is transformed, that is transformation of V1, it is resulting in W1. Transformation function applied on V2, it results in W2. Transformation of V1 plus V2, it resulted in W1 plus W2. Transformation of A dot V is equal to, it results in A into W. So here we'll take some problems on the linear transformation. So here let us assume D as the differential mapping from Pn to Pn minus 1, where Pn is nothing but a set of polynomials of degree n, and Pn minus 1 is the set of polynomials of degree n minus 1. So where we can represent D is such that Pn is transformed to Pn minus 1 such that differentiation of V, it is defined as d by dt of V, then prove that D is a linear transformation. So here D represents the differential mapping. So whatever the differentiation operation you are going to perform, so we need to show that it is a linear transformation operator. So here in order to show it as a linear transformation, we had to check with the addition as well as the multiplication. So first we are going to consider the addition operation. So the differentiation on the sum of the two variables u plus v, it is written as d by dt of u plus v. So yes, since it is a plus, you can separate the differentiation. That is, we can write this as du by dt plus dv by dt. So here du by dt is nothing but the differentiation of u, plus dv by dt, it is represented as d of v. So here you can see that differentiation of u plus v, it is equal to d of u plus d of v. So here whatever the first condition we have taken, t of v1 plus v2 is equal to t of v1 plus t of v2. T, it may be any function as I told. So yes, since the condition is satisfied, so the first condition is okay. So next you have to check on the second condition, that is you need to check with the multiplication. So here you are going to consider the operation d of a dot v, so which is equal to d by dt. In place of just v, we are writing av. So here a is a constant, you are going to take it outside. So here you can write a dot dv by dt, which is equal to a into d of v. So here once again the scalar multiplication operation is also satisfied. So since the two conditions, addition as well as the multiplication conditions are satisfied, so here we can consider D, the differential operation, as a linear transformation function. And similarly, so here we are going to check with the integral operation. So here we are going to consider I such that V is transformed to R be the integral mapping, which is defined as I of V is equal to integral 0 to 1 V of t dt. Show that I is a linear transformation. Once again, the same operations you are going to apply here. I of u plus v, which is written as integral 0 to 1. In place of vt, it is written as u of t plus v of t into dt. So since plus operation is there, you are going to separate the integrals. That is, you can write it as 0 to 1 integral u of t dt plus integral 0 to 1 v of t dt. So here this represents I of u plus I of v. So the first condition is satisfied. Similarly, we are going to verify the multiplication. So a is a constant. So I of a dot v, it is written as integral 0 to 1 a dot v of t dt, which is equal to a is a constant, take it outside the integral. So a into integral 0 to 1 v of t dt. So which is equal to a into, so this whole thing represents I of v. So yes, since both the condition, addition as well as the multiplication is satisfied, so we can also say that integration is also a linear transformation. So when you given the differential operation as well as the integral operation, so you just show these steps and explain and mention it as a linear transformation function. And next, we are given with I as I is such that V of R, which is transformed to V2 of R, be a mapping for the function f of x is equal to 3x comma 5x, show that f is a linear transformation. So here given this function, so we need to show f as a linear transformation. So the first one is we are going to consider in the place of f of x as f of x1 plus x2, which is written as 3 into, in place of x, replace it by x1 plus x2. So here we'll be getting 3 into x1 plus x2, comma, similarly 5 into x1 plus x2. So here multiply the terms. So here we'll be getting 3x1 plus 3x2, comma, 5x1 plus 5x2. So separating the x1 terms and x2 terms. So here we'll be writing it as 3x1, comma, 5x1 plus 3x2, comma, 5x2. So here 3x1, comma, 5x1, it represents f of x1 plus this represents f of x2. So here the addition operation is satisfied. Similarly, you can also verify the multiplication. That is f of a dot x. It is written as 3 into ax, that is in place of x, you are going to replace it as ax. So 3 into ax, comma, 5 into ax. So which is written as 3ax, comma, 5ax. And here a is common, so you take a outside. So here we are going to write a within the bracket 3x, comma, 5x, which represents fx. So here f of a dot x, it is written as a into f of x. So since both addition and the multiplication properties are satisfied, we can say that f is a linear transformation. And next one example we'll take in order to show that as a non-linear transformation function. So here it is given that f is such that v2 of r is transformed to v2 of y, v2 of y. So here which is defined by f of x comma y is equal to x plus 6 comma y plus 2 is not a linear transformation function. So here we are going to consider f of x in place of f of x comma y, we are going to write it as f of x1 plus x2 comma y1 plus y2, which is equal to, so here also in place of x and y, you are going to substitute it as x1 plus x2 and y1 plus y2. So here on the right hand side, this equation x plus 6, it is written as x1 plus x2 plus 6 comma y plus 2, it is written as y1 plus y2 plus 2. So in the next step, so here we are going to separate this x1 plus 6 comma y1 plus 2 plus x2 plus 6 comma y2 plus 2. So now considering adding the relevant terms, so here we'll be getting x1 plus x2, 6 plus 6 is 12. So here it is resulted in x1 plus x2 plus 12 comma, similarly the second term is equal to y1 plus y2 plus 2 plus 2 is nothing but 4. So here you can see that, so it is not equal to, so here this cannot be written as f of x1 plus x2. So since we have on the right hand side x plus 6 and y plus 2, so it is not equal. So here we can say that the addition property itself is failed. So here no need to go for verifying the multiplication property. So here you can say that the equation 1, whatever we have taken equation 1, it is not equal to equation 2. The values are different. So here we have x1 plus x2 plus 6 and here we have x1 plus x2 plus 12. So since the constant values are different, so we cannot say that the addition property is satisfied. So here you can mention that f is a not linear transformation function. And the next one is kernel of t and image of t. So here suppose if we consider t as, just a minute. Yes. T as a linear transformation from V to W, the kernel of T or kernel of T, that is nothing but the dimension you are going to write. So as V belongs to V such that the transformation V is equal to 0, where 0 belongs to W. So here the kernel of T, it is also known as the null space of T. And here image of T, which is simply written as image of T, img of T. So it is defined by W belongs to W such that W is equal to transformation of V for some V belongs to V. So that we'll see while solving the problem. The next one is the rank of T and the nullity of T. So rank of T, as I told, it is nothing but the dimension of image of T, and nullity of T is nothing but the dimension of kernel of T. And here suppose if V is the finite dimensional, then we can write that the rank of T plus nullity of T is equal to dimension of V. So actually this equation we have seen in the nullity rank nullity theorem. So rank nullity theorem explain ಮಾಡಬೇಕಾದ್ರೆ I have told. So the total number of columns in a given matrix A, it is equal to the sum of rank of the matrix plus the null space of the matrix. So the same expression it is going to be defined here. And the next concept is orthogonality. So here I'll just give the definition of this, and we'll take one problem on this. So here orthogonality, in order to define this, hold on. So here, before looking at the orthogonality, first we'll see the orthogonal matrix. So orthogonal matrix, it is usually considered as a symmetric matrix. So in which all identity matrices, they are considered as the orthogonal matrix. And also here the transpose of the orthogonal matrix, it is also an orthogonal matrix, and the determinant of orthogonal matrix always it will be equal to plus or minus 1. And here considering that definition, so here we can go for looking at the orthonormal set and the orthogonality properties of the vectors. So here we can consider, the orthogonal between the two vectors. So here we can consider two vectors, and they're said to be orthogonal if they're perpendicular to each other. So as we know the meaning of orthogonal, orthogonal represents the perpendicular. So here when two vectors are perpendicular to each other, then we can say that they're orthogonal to each other. And in order to verify that, so here we can take the dot product of two vectors. So here always, suppose if the dot product of two vectors, it results in 0, then you can mention that the given two vectors are perpendicular to each other. And with this, so here if we consider u1, u2 up to un, if they are acting as a pairwise orthogonal vector, then the vectors u1 up to un, they have a unit length. Unit length in the sense, as I told, they can have the maximum magnitude plus or minus 1. So here only considering the magnitude, you can mention that these vectors, they will be having a unit length, and then this u1 to un, they are going to form an orthonormal set. So that is that is the dot product of two vectors ui dot uj, it must result in 0, where I is not equal to j. So if the dot product of two vectors is 0, it indicates that these two vectors are orthogonal pairs. And similarly, if you take the dot product of same vectors ui multiplied with dot producted with ui, then it results in 1. And in other words, you can write that ui dot uj, it results in the value 1 if I is equal to j, and it results in the value 0 if I is not equal to j. Or in terms of delta, you can write this as ui dot uj, it is equal to delta ij, where delta ij is 0 only if I is not equal to j. And if I is equal to j, then delta ij, it takes the value 1. So here this condition, it has to be used in order to check whether the given set of vectors are orthogonal pairs or not. So here for this we have given one problem. So here u is defined as 1, 2, 2, v it is defined as 2, minus 2, 1, w it is given as 2, 1, minus 2. Then we are asked to check whether u, v, w are pairwise orthogonal vectors. So pairwise orthogonal vectors in the sense, first you are going to consider uv, then vw, then uw. So here in order to check the orthogonality property, so here you just you are going to take transpose of one vector, because in order to have the dot product, so we should have the what matching between the column and the rows. So here taking the transpose of u, so here it results in 1, 2, 2. So take the dot product of u transpose with v. So you can see that 1 into 2 is 2, 2 plus minus 4 plus 2, it results in 0. Similarly, v transpose w. So here you can take that as 4 minus 2 minus 2, that is also 0. So w transpose u, so here once again it will be resulting in 0. So here if you want the calculation in the notebook, we'll just solve the same problem in the next class. So the remaining problems and the last theorem we are going to look in the next class. So all of you can leave the meeting. Thank you.